Hello, everybody, and welcome to the future of machine learning in autonomous cars. My name is Maciej Dziubinski. I'm a machine learning engineer working at a company called Equinix, which specializes in data centers, colocation, and edge devices. I'm a member of Opium, which is an organization you can look up online, and I am the editor of Acta Schola Automata Polonica, which is a blog, and I've written a bunch of blog posts I'm going to reference throughout this presentation. Let's begin. The agenda for today is, first I'll introduce myself, then I'm going to say what the fundamental problems in autonomy are. We're going to go through those that I deem the most important, which is perception, localization, planning, control. And then I'm going to say a few words about future directions. Actually, we're going to focus on one future direction because it turns out that it's better to be less is more. Let's keep it at that. Right. So I did a PhD in biophysics, which doesn't have anything to do with autonomous cars, if you don't know. So once I finished, I figured I'll do self-driving cars. That's something very different. So I did a course on Udacity called the Self-Driving Car Nanodegree, which gives you some fundamentals. But I did understand that that's not enough. I have to push forward. So along with Karol Majek and Łukasz Tyber, we created a team and participated in the F1 10th competition, where we took the first place in this competition. Here's the car that we used. His name is Dzik. And here we're driving in a corridor, and I didn't speed up the video. The car is actually going that fast. And I think it's pretty impressive. I think it's awesome. So I also did some projects in the Carla simulator, which is an open source simulator dedicated to self-driving cars, and it's built on top of the Unreal Engine 4 gaming engine. So you can modify it in any way you want. And in particular, what I did, I created a racetrack, and I drove around that racetrack with a gamepad. I also wrote some controllers that control the car and drove around the racetrack. And I trained a neural network to clone that behavior. That's called behavioral cloning. And this is how the car drives around the racetrack. This is actually a neural network controlling the car. So it's something. It's driving. But I also did a different project in which the task was to take as input the side cameras mounted on the car and predict how the surroundings of the car look like. So it's sort of a projection model. And we're going to talk about that more. This is how the output from the car looks like. The left one is the ground truth, and the right one is the prediction. I'm not mentioning here what type of input is. That's going to be further down the road. I also built this small car inspired by the F1 10th competition. I built this small car which has, it doesn't have a lidar, but it has a depth camera on board. And I trained a neural network to drive around the pond that's next to my house. This is it driving. It's going faster than I anticipated, so that's the reason behind the shaky cam. Yeah. But more recently, I'm a member of a team called EuroRacing Team, which comprises 3 guys from Poland, Karol, Łukasz, and myself. 15 or so people from Italy, 15 or so people from Switzerland. So it's a multinational team. And the Indy Autonomous Challenge is a 1.5 million prize competition where a bunch of teams are going to drive at the same time on a racetrack, and the racetrack is Indianapolis Motor Speedway. And the task is to go as fast as possible. That's simple enough, and obviously not to crash. Here's the website, or rather a LinkedIn site of our team. If you want, please follow, and you'll get the latest news, and you will get to know us. And also, that's going to help us with promoting the team. Okay, that's a few words about myself. Maybe I'm going to go full screen. Can I go full screen, please? No. Okay, whatever. Okay, so here are the fundamental subproblems in autonomous cars. So we have perception, localization. Those two are on top. So these two provide input to the planning node, and the planning node provides input to the control node, which is at the bottom. So I'm not going to dwell too long on that, but keep this image in your head when I'm going to go through perception, localization, planning, and control, and the subsequent slides. So perception and machine learning. So this is probably the best subproblem for machine learning. So what is perception? So perception is taking in the sensor readings that you get from cameras, lidars, radars, sonars, IMUs, GPUs, you name it, and try to present the information that you're getting in a more ingestible form, so that the planning node later on, or rather down the road, has an easier way of task of providing or proposing a path to follow. So you have to know where the other agents are, what kind of traffic signs there are, what the speed limits are, what traffic lights there are, pedestrians, everything. And here are two examples. One, this is one approach to perception, where when you're doing panoptic segmentation, so you're distinguishing what type of classes, pixels that you see are, and also you're distinguishing between instances of those classes. So, for example, you're distinguishing that this car is not the same as the car that's like next to it, so it's a different instance. A different approach to perception. So this is a part of a presentation that Andrei Karpathy did. He works for Tesla. So this is the output from the perception stack. So notice that this presentation is from February 2020. So this is how it looks like. And I mean, like, I don't have much to add. It's just obvious how good this project, or rather how good this problem is for solving using machine learning, provided that you have labels. And even if you don't, you can try and do something with unsupervised or semi-supervised machine learning. And one aspect that I think is very exciting are these event cameras. So these are cameras that have no motion blur, because they actually register the changes that are happening at a very high frequency. And this is the information that they actually produce. Notice that this information is sparse. So in other words, these cameras are awesome for estimating depth and VisualSLAM, which I'm going to say a few words more later on. But because the information is sparse, it doesn't make sense to use a standard dense, in a sense, convolution. It's better to have convolutions that focus on those areas in the image in which actually something changes. So this video is actually for a paper that produces those sparse convolutions that work in those on input from those event cameras. And I think that's very interesting, that sort of something that's going to push machine learning and autonomy further, or generally, are different types of sensors. So it's always good to have a look into what's currently being developed and what's coming in the upcoming years. That's how you say it. Right. So this is perception. Localization. So localization, I would say, is a no machine learning subproblem. Probably it's not, but it's. I'm going to go on a limb and say that it's pretty much solved. It's solved in the sense that we, as a team, the F110 team, had certain input. We had lidar readings, and all we had to do is just find the right project on GitHub that provides you with localization using particle swarm, where as input you get the map, you get those readings from the lidar. So those color points are the lidar readings. And you have a bunch of those hypotheses of where the car is. I'm not sure if you can see that. Where the car is, those small arrows here. And averaged out, those arrows provide you with this large arrow that gives you the orientation and your position, like the position is the beginning of the arrow. Rather the end of the arrow, I think. But anyway, so it's a done problem in the sense that in standard environments, standard situations, you have a readily usable tool available to you. But something that I think might, and I'm sure that does benefit from machine learning, is SLAM, and in particular VisualSLAM. So SLAM stands for simultaneous localization and mapping, meaning that you get your sensor readings and you create the map as you go. So you, at the same time, you have to know where you are in the map that you are currently building. So how it looks like, here's an example. I'm using a VisualSLAM to create a map of the pond that's next to my house, around which I was driving the car. So you get these, because this is a depth camera, so you have this depth input, you have the RGB, and from those two you get those point clouds. And the task is to stitch those point clouds together in such a way that at the end you get a map of the environment in which you are. So obviously, this area can benefit from machine learning, and it does benefit from machine learning. And I've seen results provided by companies and researchers, and it seems like a pretty decent. It seems to work pretty decently. Mainly indoors. Outdoors, I think it's pretty hard. But also, you can imagine that you can take those point clouds, stitch them together in such a way that you provide a mesh, a three-dimensional mesh of, I don't know, of your room or whatever, and combined with VR. That, that's the future. But you get the idea. So that's, I think, interesting in localization. So remember, we have localization and perception, and those two provide input to planning. So planning takes that ingestible information in, as well as the map, because you have to know where you are on the map, and the positions of other agents on that map. And by agents, I mean other cars, pedestrians, and everything else. And the task in planning is to come up with a path that sort of is safe, that gets you from point A to point B, or that guarantees that you're going to take the left on the next crossing, whatever. And the planning is more about, it's not navigation. It's not like how to go from Poznan to the torso. It's more in terms of your local environment and what's happening right now. And what it requires is motion prediction. You need to know what's going to happen. You need to anticipate what other agent is going to do if you want to have a safe path forward or whatever. So this is a pretty, I'm not saying that it's recent, but there are recent developments which are very interesting. Like, for example, there's this competition, Argoverse, which is an ongoing competition. You can take part in that. Currently, I think the best approach has it's a LSTM with attention. So, obviously, someone's going to come up with a transformer and have a better prediction. And there's also this ongoing competition on Kaggle. There's 1 month left from Lyft. So this image at the bottom is actually from this Kaggle competition. The one on the right is from this Argoverse dataset competition thing. And the Kaggle competition, it focuses on those two images in the center. So what you have as input, you have information about all the agents, where the lanes go, et cetera, et cetera. And what you need to predict is what's going to happen in the future. And once you know that, once the planning takes that all into account, and it provides you with a path, proposition to follow, you have to follow that path. So this task is actually called control. So given a set of waypoints, sort of like these points that you have to go through, check as in a game, how should you control the steering angle and the throttle so that you go through them? It seems simple enough, but it actually is pretty hard. And I'm not talking even about scenarios where the road is wet, or there's ice or whatever else that is extreme. I mean, like, normally the car is a pretty sophisticated dynamical model, and people do it naturally, but it's actually pretty hard if you want to do it like a systematical manner, programmatically. So this is typically framed as an optimal control problem. And optimal control theory is a branch of mathematical optimization that deals with finding a control for a dynamical system over a period of time such that an objective function is optimized. So this is perfect. This is a perfect setup for reinforcement learning. And the second video that I wanted to show you here is this promotional video for a paper called Superhuman Performance in Gran Turismo Sport using deep reinforcement learning. So they are using a soft actor critic, and they compare themselves with other players, which I think are the best in the world. So it's pretty impressive. And I'm surprised that no one had much success in this field previously. And maybe one of the reasons is that there's it's a difficult problem, meaning that two inputs that are very similar actually should provide a very, very different outcome. So the model needs to distinguish between those two. Yeah, so I think it's called state aliasing, or aliasing is a problem. I don't remember. I'm not an expert on reinforcement learning, to be honest. But what I am sure of is that this area will benefit from reinforcement learning in the future, particularly reinforcement learning that explores in a safe manner. And yeah, and one thing I wanted to add is that I wonder if they compare themselves not to a human, but actually to an optimal control algorithm, would they also be better? Because from I've heard from a lot of experts in control that the optimal lab problem is pretty much solved. I mean, you're not going to get like all the nitty-gritty details, like that there is different friction at different parts of the track, et cetera, et cetera. But you can come up with a pretty sophisticated dynamical model of the car, and you have pretty sophisticated and well-working optimizers. It seems that nothing stands in the way of this being a solved problem. Obviously, it's not, but it's very close from what I gather. And yeah, and I wonder if the reinforcement learning agent would perform as well when compared to an approach like that. OK, so we have an overview of the autonomy problem. So what are my thoughts on future directions? One direction, actually. I wanted to focus on one, which is a sort of manifestation of a more general trend. So the general trend is that cheaper and more specialized sensors are going to emerge, and they are going to push the boundaries of what we're currently doing and what we're going to be doing in the future. Cheaper because it has to be accessible to a broader audience, and more specialized because it's just going to provide you with better input than those old sensors that we're currently using. And so cameras are pretty cheap, and they do provide you with information that you can sort of provide you with more information that you can handle. This is a far-fetched argument, but people are using only their eyeballs to maneuver a car, and they're doing a pretty good job. They also take into account all the contextual knowledge that they gather throughout their life, and the general intelligence that's somehow hidden in all that. But we have the same input. Well, let's come up with the contextual knowledge. How hard can that be? But outside of that approach, where you're going to solve the general intelligence problem, you can take in the input, camera input, and modify it or project it or do something with it in such a manner that it provides cleaner information or more digestible information to the planning node. One approach that I actually used in a blog post I'm going to reference right now is from semantic segmentation to semantic bird's eye view in the Carla simulator. The approach here is that you take as input those 4 camera inputs. And I have to mention, I'm using semantic segmentation ground truth. Semantic segmentation as input, because I just wanted to see if I can do the projection right, if I have all the necessary information. And the idea is to provide an output. Again, this is the ground truth of the top-down view of the car and its surroundings. This video shows, this is the input. It's low quality, sorry about that, but this is the input. This is ground truth. This is how it looks like. It's a simulator, so you can attach the camera wherever you want, and I attached the camera 15 meters or so above the car. And so this is ground truth in terms of semantic segmentation, and those are the predictions of the model. I'm not going to say too much about the model. It was pretty crude, and obviously you can try and do homography and just stitch those images together. What you get from machine learning is sort of a better way of guessing what's behind a certain obstacle. So if there's a car standing right next to you, but you know that previously you saw a tree behind, or well, you see a tree, but if you saw a person behind the car, you can sort of try and transfer that knowledge from the previous frame and infer that there should be a person behind the car. Even if you don't see it, it should be there because you saw it in the past. I'm not saying that my model was as complicated, but that was my rationale for using machine learning. Okay, and in this approach, when you see what's the car's surroundings, you can come up with a pretty decent path. And that's actually what I did in a very, very simplified manner. I'm just proposing a path that goes where it can go, where where there aren't any obstacles. So actually, the car is not following the path. I should also say that. This is just a proposition, but those white dots, those are the waypoints that sort of describe the path that needs to be followed. And it does a pretty good job of trying and maneuvering around the cars, like in the moment that we saw right now. And what I'm getting at here is that what you can do is you can take those cheap sensors that you have and try and manipulate them in such a manner that the information that you provide later on is more accessible and easier to reason with. And obviously this requires more work. This is just a proof of concept, but you might ask yourself the question: is anybody else using this? Like, it's very cute that I've written this blog post, but is anybody using that? And this is again the presentation by Andrej Karpathy from Tesla. I have a better problem, a better idea. Let's.
So you have to somehow project this out into a bird's eye view sort of.
I wonder if you can see him.
So the raw detections, we project them out into 3D and we stitch them up into what we call a occupancy tracker. So this occupancy tracker takes all the raw measurements from the 2D images, we project them out into the world, and we stitch them up across cameras, and we stitch them up across time. So the occupancy tracker is keeping the temporal context of that, and it creates a small local map, and then it winds its way through the parking lot to get to the person who is summoning the car at this time.
Right. I'm not sure if you heard what he's saying, but this is generally the same idea, that you're taking in the side cameras and you're coming up with this bird's eye view so that it's easier for you to maneuver. This is a parking lot, but generally it's easier to maneuver in the environment on the road. So yeah, this presentation is from February 26, 27. My blog post is from May 2019. I'm not saying that they got inspired by my blog post. I honestly doubt it, but it does show that it's pretty natural direction of, you're thinking in terms of a top-down view anyway, because the planning and the control, everything that works in a sort of in a top-down view manner, a top-down view world. So why not just try and come up with that representation to your planning and your control algorithms? So it's a pretty natural direction. And it's awesome that Tesla uses that, but what, like any other companies, and yes, there is a company called Audubon, and I'm in contact with Christian Gebis, who is one of the co-founders of this company. This is the website. So they're focusing on trucks, and they're not particularly interested in a fully autonomous trucking system from the start. What they're actually aiming at is an assistance service that's gonna provide some information, valuable information to the truck driver, which he doesn't have as easily accessible because he doesn't have an eye behind the truck. He has a camera behind the truck. But if you're looking at too many camera readings, you're not going to get much. You have to condense that information. And so Audubon is a company. This is from their official website. Will transform existing trucking fleets into the most advanced and safest transport service providers to offer unparalleled efficiency and security. I also asked Christian to give some overview. So Audubon is building a hardware and software that simplifies, streamlines, and automates freight deliveries. That's what he says. And also what he says is, we are looking for extremely talented mathematicians, computer vision, deep learning, and photogrammetry experts to join our engineering team in Warsaw. So this is a shameless plug here. If you want to learn more, reach out to Christian or Christian. Here is his email, and yeah, and that's something I'm very excited about. So this last video is not on YouTube; it's top secret. It's a promotional video that sort of summarizes the type of input that you're going to get mounted on the truck. So bear in mind, those are cameras. So you have cameras mounted. Well, I'll let the movie describe it better than I do. So this is the type of information you're going to get. And I think this is more of a question to you guys. What do you think? What kind of things you can do with this type of input? Also, you have a camera inside the truck to monitor what's happening inside. Yeah, reach out to Christian. I think it's interesting. I think that there are multiple directions in which autonomy and machine learning can go. This is just one of them, and I think it's a very interesting, very exciting direction. Yeah, that's pretty much all I could say. Thank you for your attention. If there are any questions, I'm more than happy to answer them. And yeah, thanks.
Hello.
Hello.
So, hello. Thanks, Maciej, for this great presentation on a topic that is in the very forefront of robotics and computer science and computer vision, and of course, machine learning. And now we would like to ask a couple of questions. We are a little bit delayed with this session, but we still have a time to ask. There are two questions that are pretty related from the same person, so I will concatenate them. The first one is the biggest issue with self-driving cars are edge cases. 20% of work create 80% of the results. Do you think that we can achieve fully self-driving cars by focusing mainly on these cases? And the follow-up question is, do you think that Tesla's strategy of collecting rare cases is enough to create 100% self-driving cars, or maybe we need general AI?
Right. So the question is, I can hear my voice. I wonder if everybody else can hear my voice again. But anyway, 100% self-driving car, I think not. They recently, I think yesterday or the day before, they released a fully self-driving car, so a FSD system, which is in beta and for selected consumers. And it does drive around in neighborhoods and larger city and larger intersections, something that I thought that is very, very difficult. So they managed to do that more quickly than I was anticipating. I agree with the sentiment that without having enough edge cases and sort of encountering an edge case that you've never seen before might be an issue. But there are solutions to that. Like, for example, just stop the car, don't do anything, or drive off not drive off the road like completely, but drive to the to a safer place and wait for whatever obstacle that you're seeing to sort of change, or let the driver make a decision. That wouldn't be 100% a self-driving car, but that would suffice to have a safe solution. So, and my answer to this question is not 100% self-driving car, but a 99.9% self-driving car, which may be sufficient in some sense, but that's not full autonomy, I think. Yeah.
Thank you very much for the answer. And the next question is pretty technical. Are there any solutions to bad weather? Because it can be very harmful for sensors.
Yeah, one of the most, I think, known accidents of Tesla was when they encountered a solar flare. I'm not sure if that's called. It's called. I mean, the flare where the camera is directed at the sun and it sort of makes the image light up too much. And there was a truck in the way that was completely white, and there was a collision. I'm not an expert on sensors, so I have to go on a limb here and say that there are ways of sort of making sense of the sensor readings when the weather is bad, but most likely than not, there are times where you will need to be able to discern that something isn't right and that the sensors are not working correctly, and have a sort of a safeguard, or I don't know, a way of coming to safety even without all the sensors, just having some of the sensors. And maybe I would guess that if all the sensors are out, you have to sort of be able to maneuver in the map that you created or the map that you have right now and sort of stop in a safe way. So again, I'm not an expert on sensors, but I think that people are have a bunch of solutions, not all of them, but the vast majority.
Okay, thank you very much for the answer. And the last question I see here in our application is, do you think that planner returning control points is enough in contrast to the planner which plans paths trajectories to follow?
Yeah. I actually tried both. I tried the sort of an MPC, a model predictive control, where I only have the waypoints, and I know that I have to drive as fast as possible because I was interested in a race car. And I also tried out a different one where I sort of dictated to the model, to the actuators, sort of do this in this particular instance, have throttle at this level, and have, or rather, it was velocity. Keep the velocity at a certain level with a PID, and follow a certain trajectory. The MPC worked better for me, but I know that people are, like, for example, the Technische Universität München, they are actually using this two-stage controller where they first come up with the waypoints and then they come up with the whole trajectory. So they sort of fill out the waypoints with information that provide them with the full trajectory, and then they follow that.
Okay, thank you very much. And there is one question more that just appeared here in UVA. It is, do you think that we could use a few systems inside the same car and check if they agree each other if it comes to steering decision?
I'm going to guess that the question is, what about the sensor fusion that everybody's using in terms of making the decisions? So is it possible to have sensor fusion when coming up with the decisions? So let's say that we have two systems, they provide two different types of sort of proposed different paths to follow. Can we stitch them together depending on the environment? I didn't see a solution like that, but that's something I think that a lot of people was thinking about in terms of having systems more sort of fine-tuned for certain situations. So let's say we have one planner that always yields a path that's super safe. Like, for example, you have a planner that's super obsessive and he's thinking that everything's going to go high-wired any second. You need to be able to find your way to safety at any moment. So you have this one planner. You have a different planner that sort of assumes that everything is going to be fine. And you can sort of have a third, maybe not necessarily a planner, maybe a level on top that's making the decision which of those two planners should be used. I'm pretty much sure that, I'm not a roboticist again, but I'm sure that roboticists, they do in terms of artificial intelligence in particular, not necessarily in terms of machine learning and database sort of solution, but more modular solution where you have those subsystems that talk to each other, and you can have this at some level of communicating with those systems. There's this assumption that intelligence emerges, and you can have, if they talk together, you can have very intelligent sort of decisions. I am aware that there are these ways of thinking about AI as an intelligence stemming from multiple smaller, pretty primitive components, and by communicating with each other, they come up with very intelligent solutions. So I know that there are people working on that. I just don't know if Tesla is using that. I don't know if Waymo is using that. I wouldn't say that I have any reasons to think that they do, but they seem to be very secretive about their developments. So it's, my guess is good as any, and my guess is that they don't have a sophisticated system like that. Maybe a two-planner, like a safe planner and a normal planner, I think yes, but not like in terms of a super complicated decision fusion module or something like that.